again. It is time to talk about the famous paradox of the twin siblings. This is a paradox introduced right after Einstein presented his theory of relativity. He used to call it the clocks paradox. Imagine there are two siblings on Earth. One of the twins decides to go and explore the universe, takes a spaceship and travels to our neighboring star system, Proxima Centauri, 4 light years away, at the speed of 80% the speed of light. Here on Earth, meanwhile, the twin sibling stays on Earth. Let's stay with the sibling on Earth first. Because of time dilation, the sibling on Earth sees how the traveler has her time dilated, so time will be slowed down for the traveler. From Earth, the sibling sees that the traveler at beta equals to 0.8 will take 5 years to reach Proxima Centauri. Gamma for beta equals to 0.8 is 1.67. This is the time dilation factor. So from Earth, we see that during those 5 years, the traveler has only aged 3 years. Once the traveler arrives at the planet, she stays there for 1 year. Because both planets are at rest with respect to each other, then we can consider they are in the same inertial frame. So no relativity effects while at the planet. After 1 year, the traveler decides to go back to Earth. The return journey is the same. 5 years from Earth, but 3 years for the traveler. So as measured from Earth, the time elapsed is 5 plus 1 plus 5, 11. But the traveler has only aged 3 plus 1 plus 3, which is equal to 7 years. So there is a difference in age of 4 years. The traveler's sibling will be younger than the sibling on Earth. So far, so good. Now let's look at this journey from the traveler's point of view. For the traveler, she is at rest in her inertial frame. It is the sibling and the whole Earth and the whole universe that are moving back. For her, time is not dilated, but time for the sibling on Earth is dilated. For the traveler's sibling, the sibling on Earth will travel back at 0.8 c, stop for 1 year, and then return at 0.8. It is the sibling on Earth that experiences the time dilation and the one that ages less. For the traveler's sibling, she will be older than the sibling on Earth. When they meet back, who's younger, who's older? It can't be that both are younger and both are older at the same time. Is the theory wrong? Did we miss anything? Did we apply correctly special relativity? Well, the relative speeds are the same. We apply time dilation to the moving observer with respect to the one at rest. Better, let's have a look at the spacetime diagram. So let's do this spacetime diagram analysis. We have beta of 0.8, therefore gamma is 1.667. Now, light travels with 45 degrees as always. For the traveler sibling, because beta is 0.8, we calculate that for a distance of 4 light years, it needs 5 years to travel to reach to that star in the Proxima Centauri system. Now, stays 1 year there, so 6 years have lapsed on Earth and then comes back. So it's 5 plus 1 plus 5, it's 11 years traveling there. Okay, now we need to calibrate the axis of the traveler. Remember how we did that in the spacetime diagram with the hyperbola. So in this case, the traveler will reach the destination after 3 years of her own time. Will spend 1 year in the planet and then will spend 3 more years of her own time coming back to Earth. If they decide to say happy birthday every year, well, the sibling on Earth will send one message saying happy birthday after the first year, but because of this time dilation and the fact that the traveler is going away, that traveler will receive that message after 3 years of her trip. Then the second happy birthday will be just 1 year after, because that year is spent on the planet, so both planets Earth and that planet at Proxima Centauri are in the same reference frame, so 1 year here is 1 year there. Then the next 3 messages will be arrived in just the one period of 1 year, because now we have that the traveler is coming back to Earth, so those 3 pulses of light saying happy birthday will arrive at a shorter time in this case, and the next 3 will arrive also in the next year for the traveler, and the same with the next 3. Now let's have a look at from the point of view of the traveler. We have the axis calibrated. We have that spends 3 years going to Proxima Centauri, 1 year in Proxima Centauri, and 3 years coming back from Proxima Centauri. Now, the traveler also is going to send a message every year to the sibling on Earth. So the first will be after 1 year, 1 traveler's year, which will arrive after 3 years on Earth. The second is after 2 years traveling will arrive at year 6 on Earth. The third will arrive here on Earth after the 9th year. What about the last 3? Well, the last 3 messages, which are sent every year, will arrive with all those 3 in just 1 Earth year. So we see here that the traveler has actually just lived 7 years, while the sibling on Earth has lived 11 years. By looking at this spacetime diagram, we can see that the problem is not symmetric. The sibling on Earth stays in an inertial reference frame all the time, but the traveler's sibling does not. The traveler changes of inertial frame. The traveler needs to accelerate to reach the cruise speed, then decelerate to land in the planet by Proxima Centauri, then accelerate again, and then decelerate again to end up being at rest on Earth. Each sibling has a different experience. The traveler experiences acceleration, which is what breaks the symmetry of the problem. In the spacetime diagram, we assumed that the traveler gets to 0.8 instantaneously. Okay, let's accept that. But in order to turn around, the traveler changes from one inertial frame to another inertial frame. There is where the flaw of the paradox is. Not all frames are inertial in this problem. The fact that the traveler experiences acceleration is what breaks this paradox. We will talk about acceleration in special relativity later in this course. Now, be safe, stay at home, and study relativity.